Hey everyone, my name is Nicolaus Jennings. I'm a PhD student in the Electrical Engineering Department at UTA, and my project is focused on characterizing arc flash events from ultracapacitors and MVDC capacitors. In previous work I've studied other types of electrochemical energy storage, such as valve-regulated lead-acid batteries and lithium-ion batteries. In these cases, these types of energy storage technologies are more energy dense, meaning that they store a lot more energy. Ultracapacitors and MVDC capacitors, on the other hand, are more power dense, meaning that over a very short period of time they can deliver a lot of power. And in this case, we would like to study how these effects influence instant energy and other related hazards in arc flash events. The reason we're trying to characterize these hazards from arc flash events is because the leading cause of fatalities among electric workers is in fact arc flash. However, this arc flash comes from AC systems and not DC systems, which electrochemical energy storage primarily provides. And so, as a result, efforts from the University of Texas at Arlington have been performed to begin to fill this knowledge gap of DC systems. As the Navy begins to introduce energy storage, especially up to the levels of 8 kVDC, we have been tasked to study with ultracapacitors and MVDC capacitors the instant energy, the light intensity, the sound pressure measurements, all produced from these types of events. The experimental setup utilized by UTA was not at all dissimilar from the previous experimental setup used in the past. However, the only difference was for the MVDC capacitors on how the electrical potential was brought in front of the calorimeter board and the arc in a box that was constructed around the arc point. The ultracapacitors we used 184 of them. They're rated for 2000 farads at 2.7 volts each. And we used upwards of 10 MVDC capacitors rated for 11 kVDC at 850 microfarads. Because we were able to use a box in this case for the MVDC, we also had to use one for the ultracapacitor study. The board that we used was once again composed of 13 calorimeters. In this case, we only looked at the light sensors. Previously, we had a pressure sensor, and we also had a sound measurement sensor located around 2 feet outside of the box. The reason we're studying in the box is because electric workers perform their maintenance inside of energy storage cabinets or switchgear cabinets, and as compared to an open air environment, the enclosed environments tend to reflect the instant energy that's generated inside of these and directed outwards more towards the worker, resulting in higher or amplifications of instant energy. Of course, these instant energies amplifications then result in more severe injuries. The copper bus bar that was used is directly in front of the calorimeter board, separated by 18 inches. This is also the case for the MVDC capacitors. The calorimeters, or the instant energy sensor units that we use, are copper discs, thin copper discs that are painted black and also separated from 18 inches away from the arc. Light intensity measurements are conducted with a light diode that is able to replicate the light intensity measurements for a human eye. And as a result, the intensity of the arc flashes are much greater for a human eye. So we use neutral density filters that are able to reduce down the light to something that the light diode can see, and then we're able to step that back up to the actual peak light produced within each arc. As well, the capacitor voltage, capacitor currents, the voltage across the gap are all recorded with an oscilloscope at greater than 1 megasample a second. Finally, we have high-speed imagery of the arc, and we also have high-speed thermal imaging recording the the calorimeter board directly after the arc and before the arc to provide validation for the calorimeter temperatures. Our test plan for both ultracapacitors and MVDC capacitors are as follows. Using the 184 capacitors, we could charge them up and arrange them in series up to 500 volts. And when assembled all in series, they were about 10.75 farads, giving us a total energy storage of 1.3 megajoules. 2 gap distances were studied for these. We used half an inch and a quarter inch. For the MVDC capacitors, we have many of them as shown in figure 2, but we wanted to limit our study cases up to 5 in parallel and 2 in a total of 5 banks. The 5 in parallel were only composed in a single bank, and 1 single bank was studied. For the multi-bank experiments, these are where we had multiple banks firing into an arc to make it continuous, extending out the duration. In this case, we only studied 1 parallel capacitor or 2 parallel capacitors per bank. For the 5 parallel capacitors in 1 single bank, the energy that was able to be stored was 130 kilojoules. Multi-bank studies were also studied, and as a result, those were able to store up to 250 kilojoules overall throughout the entire bank. For both energy storage types, instant energy measurements is recorded before the arc to provide a net zero, and then after the arc about 30 seconds. This then allows us to calculate the instant energy duration after the arc is extinguished to see if there are any peaks in the temperature measurements. Moving on to the arc flash experimental results, starting off with figure 3, we have our ultracapacitor measurements. Looking at the largest figure here, we see the arc duration compared against the charge voltage compared against the instant energy that's measured. The highest instant energy that we measured was 0.6 calories per centimeter squared, which falls below a arc flash boundary of 1.2 calories per centimeter squared. This arc flash boundary is established as the minimum distance, in terms of meters, that results in a second degree burn, and this second degree burn is characterized by 1.2 calories per centimeter squared. While the energy stored throughout all of these banks was 1.3 megajoules at 500 volts, the at most arc energy that was released was 191 kilojoules. Obviously, higher charge led to higher duration arcs, which produce the greatest instant energy. This, of course, falls in terms of the energy overall stored and overall released. But primarily, the energy isn't the main key factor here. It's actually the potential across the gap. The potential across the gap, once the arc is initiated, shorts the capacitors, and so as a result, there's a voltage drop inside the capacitors. If the voltage drop inside the capacitors is large enough to not be able to sustain the arc for long durations, then the arc just quickly extinguishes. But for longer durations, the arc is able to extinguish. However, at the same time, the energy inside of the capacitors is being drained. As a result, the arc voltage, or the capacitor bank voltage, also is dropping at the same time, and so you have another drop as well too in voltage, just natural from the arc instant energy. And so that is also resulting in a loss of voltage, which could be an explanation for why we see such lower energies released, but we have much greater energy stored. And then one big thing as well too is that light intensity and sound intensity increased with charge voltage as expected, but light intensity increased far more rapidly up to 500 volts, while sound intensity more so increased linearly. Gap distance did not affect light or sound intensity as shown, and the widest gap distance led to the greatest instant energy, which was half an inch. And finally, since the capacitor banks were studied throughout all the testing, the bank resistance, which is kind of an important thing for many modeling circumstances, remained constant throughout the testing. And so what this would imply is that the current throughout all of the arcs would be roughly the same, because the current and voltage just depend, or the current and voltage just depend on the arc itself and not really the system that is behind it, because the system is the constant here. Moving on to figure 4, which demonstrates our multi-bank and single-bank experiments. Our multi-bank experiments shown in figure A have two different types of experiments. We have our 1P and 2P, but we also have 1PC and 2PC. These are continuous arcs which were established by firing banks in such a way where the arc does not extinguish. 1P and 2P have semi-continuous arcs where there may be a restrike occurring because one bank did not completely finish out the arc when it was completed. And so these are just shown here for comparison. However, in all circumstances, 1PC and 1P are exactly identical to 2P and 2PC shown from this type of experiment. So continuous and non-continuous arcs generally produce the same instant energy. For the single bank experiments, we saw with higher parallel capacitance, we were able to generate more instant energy, or more energy stored enabled more instant energy to be released and studied. This also resulted in higher duration arcs. The sound intensity recovered from these types of experiments were extremely loud, amongst the loudest we have seen, and this is one of the primary hazards associated with arcs from capacitors, as the explosion I mentioned. And then as well too, the intense light that's produced was also noted as well. However, it's not as intense as what was measured for the EDLC, or the ultracapacitors that we had studied. For the single bank experiments, the greatest instant energy measured was 0.61 calories per centimeter squared. And for the multi-bank experiments, it was 0.92 calories per centimeter squared. This all, of course, remained below 1.2 calories per centimeter squared. And on average, half the energy stored within the capacitor bank overall was discharged into electrical energy in the arc. The highest total instant energy, the highest total electrical energy dispelled inside of a single bank experiment arc was 88 kilojoules, resulting in obviously the highest instant energy recorded. And in the multi-bank studies, the highest recorded energy dispelled into the arc was 161 kilojoules, and that, of course, only resulted in 0.3 cal per centimeter squared release. Sound intensity light measurements were attempted for single-bank studies, but were not attempted for multi-bank studies due to issues with capturing the data over that longer period of time. And with multiple capacitors within each bank, so 1P as opposed to 2P, the current through each of these, or the current through each of these arcs, increases more so. So at per voltage levels, you're able to generate more current, kind of study its effect on that. However, we didn't see that effect significant here at all within the sound or light intensity measurements, as they were sporadic across all the boards and were roughly close to together, and there was no real significant difference across them all. And then, of course, we've seen that light intensity rapidly increases up to 8 kVDC, as shown previously with the ultracapacitors. Finally, with some closing conclusions here, we showed that with similar electrical energies dispelled into an arc, led to different instant energies released among sources and voltages studied. And this could primarily be due to, one, the actual source behind it, or the box that we were using, as it's not completely identical to what was used for the ultracapacitors, VRLAs, LFPs that we had studied previously. Ultracapacitors and MVDCs capacitors demonstrate really insignificant energy to recommend any personal protective equipment. However, if the durations and extensions were to be made for time out to 2 seconds, this would be extremely drastic, and the personal protective equipment required for workers to wear in the event that an arc lasts 2 seconds or greater would result in instant energy or personal protective equipment for instant energy applications. And finally, arc durations from single bank experiments were nearly 1/5 the level of instant energy from multi-bank experiments at 5 times the length. So for example, at 1P we may have an arc that lasts 2 milliseconds, and at 1P we could have an arc that lasts 10 milliseconds, and you do see that the instant energy scales linearly with that time increase as a result of the multi-banks firing into a continuous arc. Thank you so much for listening to my presentation. Have a good day.